Time is a river. We all feel it flowing in one direction, carrying us from the past and into the future. It feels constant, universal, and absolute. But this is just an illusion, a trick of our perception on this one small world. Out there, in the vastness of the cosmos, time is not the same everywhere. New and incredibly precise studies have now confirmed a startling fact. If you were to place a clock on Mars, it would tick just a little bit faster than an identical clock here on Earth. The difference is almost imperceptibly small. Each day that passes on Earth, a clock on the surface of Mars gains an extra 477 microseconds. To put that into perspective, a microsecond is a mere 1/1,000,000th of a second. It is the time it takes for a high-speed camera flash to fire. It is a fleeting, almost non-existent sliver of time. Yet, in the clockwork precision of the cosmos, these tiny moments accumulate. They add up second by second, minute by minute over the course of a mission. For the scientists and engineers planning our first human steps on the Red Planet, this temporal discrepancy is not just a curiosity. It is a critical variable that must be understood and accounted for. So, what cosmic law dictates that clocks should behave differently on another world? The answer lies in one of the most beautiful and powerful ideas in all of science, Albert Einstein's theory of general relativity. A century ago, Einstein revealed that time is not separate from space. Instead, they are woven together into a single fabric called space-time. And this fabric is not flat. It can be warped and stretched by the presence of mass and energy. Gravity, he taught us, is simply the curvature of space-time. Where gravity is strong, space-time is more curved, and time itself slows down. This effect is known as gravitational time dilation. Imagine a heavy ball placed on a stretched rubber sheet. It creates a dip, a curve in the fabric. A smaller marble rolling nearby will be drawn into this curve. Now, imagine that the flow of time is like that marble rolling across the sheet. In the deep well created by the heavy ball, the marble moves more slowly. In the same way, time flows more slowly in a strong gravitational field. This isn't just a theory, it has been measured with astonishing accuracy. The GPS satellites orbiting our planet have to constantly adjust their clocks, because time for them, in weaker gravity, runs faster than it does for us down here on the surface. To understand why time passes more quickly on Mars, we must look at our solar system through the lens of Einstein's relativity. The theory tells us that two main factors influence the speed of a clock: gravity and velocity. Earth is a much more massive planet than Mars. It has a stronger gravitational pull, creating a deeper gravity well in space-time. Because we are deeper in this well, our clocks tick more slowly compared to a clock on Mars in a shallower dimple. But gravity is only half of the story. Einstein also showed that motion affects time, special relativity. The faster you move through space, the slower you move through time. Both Earth and Mars orbit the Sun, but at different speeds. Earth, being closer, travels faster than Mars. Earth's strong gravity slows its clocks. Earth's higher orbital speed also slows its clocks. When scientists put the numbers in, one effect dominates. Gravitational difference wins. Earth's stronger gravity has the larger slowing effect. Net result, time on Mars marches forward faster. That's the 477 microsecond daily gain. Relativity in action, a cosmic dance between mass and motion. The universe is a grand laboratory. The planets are its clocks. But precision matters. We need a defined Martian surface. On Earth, we use sea level. Mars has no seas, so scientists defined the areoid, a gravitational sea level. So calculations compare clocks consistently. To arrive at the 477 microsecond figure, researchers performed a symphony of celestial mechanics and relativistic physics. They could not simply place a clock on Mars and wait. Instead, they built a sophisticated computer model of the solar system. This model included the immense gravitational presence of the Sun and the positions and gravitational tug of Earth and its moon. Using this digital solar system, they could precisely calculate the gravitational potential and the orbital velocity for both Earth and Mars at any given moment. The heart of their work was applying the principles of general relativity to this dynamic model. They combined gravitational time dilation from different masses with special relativistic effects from different orbital speeds, addition and subtraction on a cosmic scale. A crucial factor is the shape of Mars's orbit. Unlike Earth's nearly circular path, Mars follows an egg-shaped trajectory, sometimes closer and faster, sometimes farther and slower. This variation causes the rate of time dilation to fluctuate. The 477 microseconds is an average. Over a Martian year, the daily gain can swing by as much as 226 microseconds, sometimes larger than average, sometimes smaller. For ultra-precise missions, knowing the average is not enough. You must also account for this predictable yearly rhythm, a cosmic pulse between the two worlds. The dynamic nature of our solar system introduces even more subtle variations, tied to synodic periods, the time it takes a planet to reappear in the same spot in our sky. As Earth and Mars move relative to one another, their changing gravitational pull causes additional fluctuations in the Martian time rate. Over these cycles, clocks on Mars can drift by about 40 microseconds, larger than expected. It shows how deeply interconnected our solar system is. The dance of planets sends ripples through space-time, subtly altering time on neighboring worlds. No model is perfect. To stay manageable, they focused on the Sun, Earth, and the Moon, omitting smaller pulls from other planets and simplifying Earth and Mars as perfect spheres. These tiny omissions can accumulate. The potential residual error is about 100 nanoseconds per day, a billionth of a second, yet meaningful over time. Even with advanced models, Martian clocks might drift a microsecond every 10 days or so, suggesting periodic corrections, perhaps every 100 days, to maintain perfect sync. In space exploration, precision is everything. Navigation systems measure signal travel times from multiple satellites. Time and position are linked. If clocks on the surface, in orbit, and back on Earth disagree, errors build fast. A microsecond can mean hundreds of meters. The difference between docking and missing, landing safely, or striking a hidden rock. Scientists envision an interplanetary internet. For it to work, every node, computers, satellites, and bases must be perfectly synchronized, accounting for Mars's average offset and seasonal swings in real time. In summary, the river of time flows at a different speed on Mars due to its weaker gravity and different orbital path. Clocks on the red planet tick faster by an average of 477 microseconds each Earth day. This is a direct consequence of general relativity, a beautiful confirmation of Einstein's ideas about the nature of space and time. The difference is not constant. It varies with Martian seasons and with the relative positions of Earth and Mars, creating a complex but predictable temporal rhythm. These findings affect critical systems, navigation, and communication, enabling safe landings and a robust interplanetary internet. We must build systems that account for this relativistic effect. The baseline numbers from these studies guide the next generation of spacecraft, habitats, and networks. We can now plan for this, setting a standard time for Mars and developing protocols to keep clocks in sync across the void. Each world has its own gravity, atmosphere, and now, its own pace of time, a unique temporal signature we are learning to chart. By measuring these differences, we are not just testing physics, we are drawing a new kind of map, not just of space, but of space-time itself. And by understanding this map, we equip ourselves to travel safely and communicate clearly as we take our first steps into the wider cosmos. Time, we are learning, is a fundamental part of our guide to the stars.